Hello everyone, welcome to OOkul. So this is the lecture number 9 on basic thermodynamics. In the previous lecture, that is lecture number 8, we discussed the second law of thermodynamics and also some of the important concepts related to the Clausius inequality, and also we saw the effect of the source and sink temperature on the performance of the devices like the COP of the refrigerator and the heat pump and the efficiency of the heat engine. So in this lecture number 9, we will be introducing a very important concept of entropy, and we will see first of all what is entropy and what are the concepts related to it. Okay, so let us begin this video. First of all, let us understand what entropy is. Let us take 2 points as point 1 and the point 2. Okay, and in this, let us first of all take two reversible paths. One path as from 1 via path A reaching 2, then B, and then 1. Okay, this is our reversible path. So in this, we know for a reversible path from the Clausius inequality, that is the cyclic integral of del Q by T is equal to 0. So we write it for both the paths, that is cyclic integral of del Q by T for the path 1A2 plus cyclic integral of del Q by T for the path 2B1 equal to 0. Okay, and this becomes our equation number 1. Now we take another path, that is 1A2C1, and this is also we are considering as reversible. So again, the cyclic integral will be 0 due from the Clausius inequality for the reversible cycle. So delta Q by T for 1A2 plus delta Q by T, cyclic integral of delta Q by T for the path 2C1 will be equal to 0. Okay, so from 1 and 2 we have the right hand side is equal to 0, so we can equate the left hand sides, or we can write it as cyclic integral of delta Q by T 1A2 plus cyclic integral of delta Q by T 2B1 is equal to cyclic integral of delta Q by T 1A2 plus cyclic integral of delta Q by T 2C1. So we have this term and this term same, so they get cancelled. So now we have, since the delta Q by T for the positions or for the points, that is the state points 1 and 2 are same. Okay, when we are going from 2 to 1 via the path B, and in this case we are going from 2 to 1 via the path C. Okay, so we know that paths are different. In this we are following the path as 2B1, in this we are following the path 2C1, but delta Q by T is same. So we know, or such kind of quantities rather, which have the same values, and the values depend only upon the starting and the end point. That this is the starting point, this is the end point, this is the starting point, and this is the end point, irrespective of the path. Such kind of quantities is known as thermodynamic property. Okay, this we have already discussed in our previous videos. So that kind of a quantity which depends only upon the state points, that is the final and the starting point, irrespective of the path, they are called as property. And this property, that is the cyclic integral of delta Q by T, but please remember, for a reversible process, is known as entropy. Okay, so entropy is nothing but the integral, or basically it should not be cyclic integral, okay, because here it won't be the cycle because we are going for 1 to 2 only. So for the any reversible path or any reversible process, the delta Q by T is known as entropy, but please remember it's only for a reversible process. Okay, but now these reversible processes are always not possible. So what happened if the process is irreversible? Let us look at that. Now we take another example in which we have the two paths, that is 1A 2B1, this one is a reversible path, and the other path as 1A 2C1, this is an irreversible path. Okay, so now we will see for different paths. For the first path, if we write, we will have the same thing, that is cyclic integral of delta Q by T 1A2 plus cyclic integral of delta Q by T 2B1 is equal to 0 from the Clausius inequality. Okay, and from the irreversible path, for this one path we will write cyclic integral of delta Q by T 1A2 plus cyclic integral of delta Q by T 2C1, and this will be less than 0. This will be less than 0. So if this is our equation number 1 and this is our equation number 2, in this we have this term and this term same, so we can write it down as, in place of this we can write the minus of this, okay, or we have minus of delta Q by T process 2B1 is equal to, or minus of this plus of, in place of this we have written the minus of this, okay, plus delta Q by T 2C1 is less than 0. Okay, so we know this 2B1 path, or rather we can write it in this form as well to make it more clear. Cyclic integral of del Q by T 2C1 will be less than delta Q by T, or rather it should not be written this way, okay, this 2C1 2B1 is this way. Okay, so now we know that this is the path, this is the part 2B1, this is a reversible path. So delta Q by T for a reversible path is already, we know, is entropy, or this is basically the change in entropy. Okay, so we know that delta Q by T 2C1 is less than ds, or we can write that ds is greater than delta Q by T 2C1. Okay, so basically for an irreversible path we have seen this is the irreversible path, and for the irreversible path the delta Q by T is less than ds, that is less than change in entropy. Or for a general process we can write, combining this one case and the previous case in the previous slide which we have seen regarding the reversible case, we can say in general that ds is greater than or equal to delta Q by T. Okay, this is the general expression. If it is a reversible case, so this will become equal to, okay, that ds will be equal to del Q by T, but if it's an irreversible case, the ds will be greater than del Q by T. Okay, so now this is for internal reversible process. Now I have summarized it here. This is for a general process. So for a general process we can write, since this side, the left hand side is greater, so we must add something to the right hand side. So we add a quantity that is named as entropy generation, that is ds is equal to delta Q by T plus entropy generation. Okay, so now some important points, let us see those. A process is reversible. When we call the process as reversible, if it is both internally as well as externally reversible. Okay, what do you mean by internal reversible? Internally reversible means that no entropy is generated within the system. If within the system boundary no entropy is generated, we say that the process is internally reversible. Okay, whereas externally reversible means no entropy is generated outside the system. If the entropy is not being generated outside the system as well, we call that process or that system as a externally reversible system. Okay, entropy is the measure of unavailable energy. Please mind this, that entropy is the measure of unavailable energy. What is availability, what is unavailability, available energy, unavailable energy, that we will be looking in our subsequent lectures. Okay, though entropy is a property, we have already discussed that entropy is dependent upon the final and the initial points, state points. So entropy is a property, but entropy generation is not a property. Okay, and it's a path function. So please remember these distinguishing points between entropy and entropy generation, that entropy is a property but entropy generation is not a property, it's a path function. Okay, now the entropy of a system can change in the following three ways. Which are the following three ways by which this entropy of a system can change? There are three ways. First one is heat interaction, mass interaction and entropy generation, in which heat interaction and mass interaction are the external interactions, okay, because these will be felt while they cross the system boundaries. Okay, and whereas entropy generation is the internal irreversibility. just note down one more important point here, that we have written one form of energy, that is heat. Okay, we have not written work. Why? Because work, kinetic energy and potential energy are totally available energies. Okay, they are totally available energies, so no entropy is associated with energy interactions in these form, because we have already discussed that entropy is a measure of unavailable energy, and since from the work, kinetic energy and potential energy all the energy can be made available, so there is no unavailable energy in them, so there is no entropy that is associated with energy interactions in these forms, that is work, kinetic energy and potential energy. Please remember this. Okay, now we move on to the entropy analysis of the closed system. Okay, this we have written a very general process or very general expression, that ds is equal to del q by t plus delta s generation. Okay, now we will take one by one cases and we will see what we get the expressions. Okay, if it is an internally reversible process means that the delta s generation, that the entropy generation will be equal to 0. Okay, will be equal to 0. So we are left with ds is equal to delta q by t. Okay, now if the heat is added to the system, means del q is positive. Heat added to the system means del q is positive. So ds will also be positive. That means the entropy of the system will increase. Okay, please remember these points, that if the system is internally reversible and the heat is added to the system, then the entropy change is positive or the entropy of the system increases. Now next is heat rejected by the system. Heat rejected by the system means del q is negative. Okay, del q is negative. That means ds, which is equal to del q by t, will also be negative. That means the entropy of the system decreases. Okay, and next is adiabatic system. Adiabatic system, you already know that no heat generation, no heat transfer takes place, that is del q equal to 0. So ds will be equal to del q by t, which is also equal to 0 in this case. Okay, so for an adiabatic system, internally reversible process followed by an adiabatic system will have no entropy change. Now moving on further, we have the case of internally irreversible case. Internally irreversible case means entropy generation will be there or entropy generation will not be equal to 0. Okay, so the general equation, the expression remains as such, that is del q by t plus delta s of generation. Okay, why I am writing it delta s? Because I told you that it's a path function, so for the path functions we write the delta s, like heat is a path function, so we write del q. Okay, whereas this s, that is entropy, it is a point function or it's a property, so we write ds. Okay, now we take the cases one by one, that is heat added to the system. Okay, heat added to the system means del q is positive. Del q is positive, so ds, which is equal to del q by t plus delta s of generation. Okay, so heat is added, so this part is positive. Okay, and whereas this entropy generation is always positive. Okay, please remember this, that this is always positive everywhere. Okay, this is not negative, so ds also comes out to be a positive quantity. Now the next one is heat rejected by the system. Heat rejected by the system means del q is negative. When del q is negative, ds is equal to del q by t plus delta s generation. So this is negative, whereas this is always positive. So this ds, that is the entropy change, it can be positive, negative or 0, depending upon the magnitudes of heat transfer and all. If this part is higher, then it will be negative. If this part is higher, then it will be positive. If both are same, then it will be 0. Okay, now we see the next case of the adiabatic system. Adiabatic system means that del q is 0. Okay, del q is 0, so ds equal to del q by t plus delta s generation. Okay, if this is 0, so this part will cancel out, and this is always positive, so the entropy change will be positive. So for an adiabatic system, if it's an internally reversible system, internally reversible, then the entropy change is 0. But if it's an internally irreversible system, then the entropy change will not be 0, rather it will be positive. Okay, so now we move forward. We see the entropy change of the universe. What is that? Let us see it. Okay, the general process we write as ds equal to del q by t plus delta S generation. This is the general expression that we have written. Okay, and we know that universe is an isolated system. For an isolated system, we always consider that the heat transfer is 0. So if this is 0, so ds becomes equal to entropy generation. Okay, this becomes equal to entropy generation, or the ds of the universe is equal to entropy generation, which is greater than equal to 0. Now comes the role of second law of thermodynamics. It says, according to second law of thermodynamics, all those processes are possible for which the entropy change of a universe is greater than or equal to 0. Okay, those processes are not possible for which the entropy change of the universe is less than 0, but those processes are always possible for which the entropy change of the universe is either equal to 0 or greater than 0. Okay, and this principle is known as increase of entropy principle. Okay, this is known as increase of entropy principle. Now we see the TS diagram. Okay, simply that equation is only one equation is used, that is ds equal to del q by t plus delta S generation. Simplifying it, if the process is internally reversible, that means delta S generation is 0, so we are simply left with ds equal to del q by t, or we take this t to this side, we get tds equal to del q, or just integrating it, we get q is equal to integration of tds. That means for an internally reversible process, we have written it here. Okay, see this becomes a kind of a diagram on a PV diagram. We just convert it into the TS diagram. How? See, 1 to 2 is an adiabatic process, internally reversible, so it becomes a line that is perpendicular to the entropy axis or parallel to the temperature axis. Okay, next 2 to 3 will be heat addition at constant temperature, so this becomes an isothermal. Similarly for 3 to 4 and 4 to 1. Okay, so now we summarize these things, that the area under the TS diagram gives heat transfer for an internally reversible process. Please remember this, for an internally reversible process when projected on the entropy axis. Please remember this. Okay, when projected on the entropy axis. Now, area enclosed by an internally reversible cycle on TS diagram represents net heat interaction. Net heat interaction during the cycle. Net heat means the heat that is being added and the heat that is being rejected. The net effect of both. Okay, and according to the first law of thermodynamics, net heat equals to net work in a cycle. Okay, hence area enclosed by an internally reversible cycle on TS diagram also represents net work. Also represents the net work. Okay, a clockwise internally reversible cycle is work producing cycle and vice versa on TS diagram. Okay, these points are very analogous to what we discussed about the work. Okay, what we discussed in the case of work using the PV diagram, they are very similar and analogous to these points. Okay, now we see the combined equations of the first and second law of thermodynamics. Okay, there are some conditions which are to be satisfied for these equations. First is that the system must be a closed system. Change in kinetic energy and change in potential energy must be equal to 0. Work done by any other process must be equal to 0. Only the work should be PDV work. Next is it should be a quasi-static process. Quasi-static process means it is taking place at a very slow rate. Okay, and it must be an internally reversible process. That means the entropy generation must be equal to 0. So for this case, we get that ds equal to del q by t or del q equal to tds. Next, tds equal to du plus pdv. This is the first tds equation we get. How? Because we know, see in this, del q equal to tds, and we can write the equation, the first law, as del q equal to du plus pdv. So from here we can write del q equal to TDS, so we write here TDS equal to du plus pdv. This is the first TDS equation. Now we know from the definition of enthalpy that H is equal to U plus PV. So taking the differential on both the sides, that is dH equal to du plus pdv plus vdp. Okay, so dH equal to this du plus pdv becomes TdS from this first TdS equation plus vdp, or we can write it TdS equal to dH minus vdp. Okay, this is the second TdS equation. So TdS equations are valid for, generally we have initially defined the condition as the internally reversible, but the thing is that TdS equations are valid for internally reversible as well as irreversible processes, and both for closed and open system. Okay, now the representation of the constant volume and constant pressure curve on the TS diagram, how we will represent them. See, constant volume means, first take the first TdS equation, TdS equal to du plus pdv. If the volume is constant, then this term will become equal to 0. So we are left with TdS equal to du. Okay, and from the definition of internal energy, we have du given as cv dt. So for drawing the constant volume curve on a TS diagram, we must find out its slope, that is dt by ds at constant volume will be equal to T by cv. Okay, this is done. Then see, for the constant pressure process, we take the second TdS equation, write it as TdS equal to dH minus vdp. Pressure is constant, dp equal to 0. So TdS equal to dH. So definition of dH is Cp dt. So the slope of constant pressure process is dt by ds equal to T by Cp. Now we know that Cp is always greater than Cv, that is the specific heat at constant pressure is always greater than specific heat at constant volume. We take the reciprocal of them, so 1 by Cv will become greater than 1 by Cp. Multiplying both sides by T, we have T by Cv greater than T by Cp. Constant volume process has the more slope compared to the constant pressure process. Okay, so constant volume process has the more slope compared to the constant pressure process. Okay, this is for the increasing temperature, and similarly for the decreasing temperature, constant pressure has the low slope and the constant volume has the more slope. So this is summarized here, that the slope of constant volume curve is more than slope of constant pressure curve on TS diagram. This is summarized here. Okay, then we see the entropy change for ideal gas. Okay, taking the first TdS equation, TdS equal to du plus pdv. Now we see, if the substance is an ideal gas, then du equal to cv dt. Okay, and the ideal gas equation pv equal to RT. So in place of this, just taking this T down, we get ds equal to du by T plus pdv by T. Okay, so in place of P by T, we can write from here, that is R by V. Okay, and in place of du we can write here cv dt. In place of du we can write here cv dt. So cv dt by T plus R by V dv. If cv is constant, that can be taken out from the integration. So now again integrating it, we get ds integration from 1 to 2 will give you s2 minus s1 equal to cv. The integration of dt by T from 1 to 2 will give you ln of t2 by t1. R is constant, taking it outside, we will get the integration of dv by v from 1 to 2 will give you ln v2 by v1. So this is the case, or this is the expression we get for the entropy change of an ideal gas, in which we know Cv and R, or basically we know the temperature of the first initial and final temperature and the initial and final volumes. But if we know pressure, what we will do? See, we will use the second TdS equation. We will get, if the substance is ideal gas, similar conditions, dH equal to Cp dt, Pv equal to RT. Then ds equal to, just taking this T down, we get dH by T minus V by T dt. So from here, this V by T can be replaced by R by P. Again doing the same thing, using dH equal to Cp dt, just integrating it from 1 to 2, taking the Cp as a constant. So s2 minus s1 will be Cp ln t2 by t1 minus R ln p2 by p1. Okay, so these are two expressions. One is when we know the temperatures, the initial and final temperature, and second one is when we know the initial and final temperatures and pressure for one case, temperature and volume for the other case. Now the entropy analysis for the open system. We know for the open system there will be mass interaction as well. Okay, and we saw that the entropy of a system can also be changed by the mass interaction. So the entropy analysis for the open system and a closed system has a bit of variation. Let us see what is it. See, this is the equation, same expression, that is ds equal to del q by T plus delta S generation, but this term has been introduced more. Okay, so mi si plus me se. Okay, So ds by dt at constant volume will give you del q by t, del q dot by t. Okay, this dot represents the divided by time. This is not temperature, this is time. Okay, plus del s dot generation plus m dot I si plus m dot e se. This is the rate, okay, divided by time. So for the steady state condition we have, that is the mass rate entering is equal to the mass flow rate leaving is equal to this, and the change, the rate of change of entropy will be equal to 0. So we can write 0 equal to del q dot by t plus delta s dot generation plus m dot si minus se. So we get delta s dot generation is equal to minus del q dot by t plus m dot se minus si. Okay, this is the expression for the entropy analysis or for the change of entropy or the entropy generation in the case of open system. Now last important term about this, that is the entropy dependence on temperature and volume. How the entropy is dependent upon the temperature and volume. See, total entropy associated with a given amount of energy, please read this statement very carefully. Total entropy associated with given amount of energy is lower at higher temperature and higher at lower temperature. That means with temperature it's inversely proportional, lower at higher temperature, higher at lower temperature. Then entropy associated per unit molecule is directly proportional to temperature, that is higher at higher temperature and lower at lower temperature. And the entropy associated with a given energy is higher if the volume occupied by the substance is higher. So just you can remember these 3 points, that total entropy associated with given amount of energy is inversely proportional to temperature, lower at higher temperature, higher at lower temperature. Entropy associated per unit molecule is directly proportional to temperature, higher at higher temperature, lower at lower temperature. And entropy associated with given energy is higher if the volume occupied by the substance is also higher. Okay, so that's all for this class. We have introduced the concept of entropy, seen the entropy analysis for the closed system, for the open system. We have understood the concept of reversibility, irreversibility, what is internally reversible process, what is internally irreversible process. We have also understood the concept of entropy generation. So in the next class we will be continuing with the concepts of basic thermodynamics. Till then, keep watching these videos. If you have any doubts, any comments, you can share them with us. You can ask your doubts in the comment section below. You can also follow us on Facebook, Twitter, and on our website. Okay, so share this video to as many people as you can so that they can also learn out of it. So see you in the next class. Thank you, take care, and have a nice day.